Now this illustration actually shows how to size the nipple according to the square inch area. Now notice the problem is just listing the number of conductors and sizes that we previously looked at in the previous illustration. So the question, we're going to be using EMT in the question. We'll have 9 number 12s, 9 number 14s, 12 number 10s, and 14 number 8s. So the first step is to get the square inch area of each of these conductors. So that means, as you know, Table 5 lists all the different insulations with a square inch area of each. So the number 12 is 0.0133 square inch area. 14 is 0.0097 square inch area. Number 10 is 0.0211 square inch area. Number 8 is 0.0366 square inch area. So in the application then of step 2, we take the number of conductors for each size conductor and do our math. So as you see, we have 9 times the number 12 square inch area, 9 times the number 14 square inch area, and 12 times the number 10 square inch area, and 14 times the number 8 square inch area. Now, each one of these square inch areas, when added up, as you see in step 2, come up with 0.9726. But we have applied step 1 and step 2 at this point. Now, step 3 is finding the conduit at 100% total fill to do our little check here. Now, the 1.5 inches in the table 4 to chapter 9 EMT has 100% fill in that column of 2.036 square inch area. Now, since it's a nipple, we can have 60% of that. So 60% of 2.036 comes up to 1.2216 square inch area. Now, is 1.2216 greater than 0.9726? Well, the answer is yes. So step 5 illustrates this. So the solution in the answer, we could use 1.5 inch nipple using EMT, and that would meet the code, and it'd be self-supported with the fittings, and we wouldn't have to derate for any number of current carrying conductors as required in our table 310.15 C as in car 1 of the NEC.